Okay, our talk of the session is by Farzan Byramji, and he's going to tell us about all bounds for new quadratic depth resolution polar variations. Please.
Yes, hi. This is joint work with Srijato Bhattacharya, Arkadev Chattopadhyay, and Rasalan Pagli also. So before talking about what resolution over parities is, let me just start with resolution. So this is a very simple proof system which operates with clauses, just ors of literals. We have a single inference rule which says that if A and B are clauses, then from A or X and B or not X, we can derive A or B. A refutation in this proof system for a formula phi is just you start with the formulas of phi and then repeatedly apply this resolution rule until you have derived the empty clause. Now, of course, the main complexity measure here is size, just the number of lines in this proof. And in this talk, we will be interested in an extension of resolution called resolution over parities. So res parity is a proof system where the lines are now ors of linear equations over F2 instead of just literals. We have two inference rules now. So we have the resolution rule, which is similar to the one before. But now, instead of resolving on just a literal, we now resolve on a linear form V. We also have the weakening rule, which says that if A and B are linear clauses such that any satisfying assignment of A is also a satisfying assignment of B, then we can derive B from A. And our refutation is defined in the same way as before. And here, so of course, the main complexity measure is the size, the number of lines, but we will also be interested in the depth of such proofs, which is the length of the longest path once you rewrite the proof as a DAG, according to how the rules are applied to previous clauses. So before saying more, let me give some motivation for why we care about res parity. So the basic system resolution is fairly well understood. We have some techniques and several lower bounds for doing this. We can even have some strong lower bounds for AC0 Frege, which is now the lines are general constant depth circuits using and or not gates. But as soon as we put in mod 2 gates, so we don't have strong lower bounds. Even though we have corresponding circuit lower bounds, we have had them for a long time. And now res parity is a very special case of AC02 Frege, where the lines are just now these depth 2 formulas, just ors of parities. But even for this seemingly simple extension, we don't have any super polynomial lower bounds on size. And but still, there has been quite a bit of progress on very restricted versions of res parity in the last few years. And I want to mention a couple of them that are most relevant for this talk. So the first of these involves the bit pigeonhole principle, which is some binary encoding of the pigeonhole principle. So I'll use m to denote the number of pigeons and n the number of holes. So for each pigeon I, we have a collection of log n many variables, which together encode which of the n holes this pigeon goes to. For each pair of pigeons and possible hole z, we have a clause saying that it is not the case that both these pigeons go to this hole z. So for this formula, Efremenko, Garlic, and Itzikson showed that any regular res parity proof must have exponential size. For this talk, it is not important what regular exactly means, but I'll just say that any such proof has depth at most the number of variables, and I'll use capital N to denote this number throughout the talk. So going beyond depth n, Alexei and Itzikson showed that there's some formula for which proofs of even depth n log n, as long as the proof depth is limited to n log n, then we still have an exponential lower bound, and this depth bound was improved by Efremenko and Itzikson to n log n for the same formula. So let me explain informally what their formula is. So for a graph G, I'll use TSG to denote the Satan formula on G. And this is some encoding of the handshaking lemma on subgraphs of G. Concretely here, the graph that we need is that it should be an expander with logarithmic degree. And then we compose the Satan formula with the 5-bit majority gadget in the standard way. So for any CNF formula psi on some y variables in gadget G, their composition is obtained by replacing each y variable by g applied to a fresh set of x variables. And now this exponential lower bound for proofs of depth n log n was basically the best known bound, and Efremenko and Itzikson had asked to prove some lower bound for proofs of depth some polynomially larger than n, and indeed that is what we do in this work. So one of our results is an improved size depth lower bound for this lifted Satan formula. And in fact, we can now take the graph to just have degree 3 instead of logarithmic. So we show that for this particular lifted formula, any proof that has depth polynomially smaller than quadratic must have exponential size. Let me mention here that since we are now working with a 3 regular expander, and our gadget is a 3-bit majority gadget, this is a 6 CNF formula with a linear number of clauses, which means that the depth bound that we can go up to is almost quadratic even in the formula size. A corollary of this pointed out by a reviewer is that any rest parity proof of this lifted formula without any explicit restriction on the depth must have almost quadratic size. Now, this is a very, very weak lower bound, but before this, there was no formula for which we knew of any superlinear size lower bound in rest parity. And we also proved similar size depth lower bounds for the bit pigeonhole principle and some variants. Here, I'll just focus on 2 of these. So we show a similar lower bound which goes up to almost quadratic depth for the pigeonhole for the principle when we have exactly n+1 pigeons. We also consider the weak setting where we don't place any restriction on the number of pigeons now, but now we can go up to depth n to the 1.5 almost. And both of these results improve upon what Efremenko, Garlick, and Itzikson had showed. In the remaining time, I want to give some high-level idea of what goes into the proofs of these. So for that, it is convenient to take the top-down perspective of such proofs. So for any formula phi, we can define a corresponding search problem. So the input to this search problem is an assignment to the variables of phi, and we want to find a clause of this formula which is set to false by this input assignment. And our rest parity proofs that refute a formula phi are basically the same as affine DAGs that solve this particular search problem. And this transformation preserves the complexity measures like depth and size that we care about. So let me say a little bit about what an affine DAG is. So these are like branching programs that query parities, but importantly, they are more restricted in that at each node, we now have a linear system which explicitly tracks what the DAG knows about the input at that point. So in the beginning, the DAG does not know anything, so it is labeled by the empty system. At the leaves, we want that the linear system at that node must on its own be enough to falsify a particular clause. And after making a parity query, the DAG may also choose to forget some of the things it knew earlier. So with this in hand, I can now describe the random walk with restarts approach of Alexeev and Itzikson for proving such size depth lower bounds. So we want to show now for some particular search problem that any size S affine DAG must have large depth. And this the depth bound we are shooting for is something like dt over log S for parameters d and t that depend on the search problem. So the way we do this is, our goal is to find some long paths in a given DAG. So the way we do this is in phases. So we start with the root of this DAG, we find some node at depth d, and then we try doing this again several times. So we want to do this, repeat this from the current node, t over log s many times. If we are able to do this, then we have shown that there is this long path of depth dt over log s in our DAG. Now, since we want to do this iteratively, we want that at this new node, if we haven't already made an enough number of phases, then the DAG must have made a small amount of progress only. So we want to explicitly track some progress measure which increases only by log s many units in a particular phase. And then we want to say that as long as only a small amount of progress has been made totally, so that up to some threshold t, then we can perform this next phase where we find a new node at depth d from the current node. And the way we do this in each phase is via random walk. This is what gives the approach its name. And to make things a bit more concrete, I will do this explicitly, or at least give some high-level idea how we do this for the bit pigeonhole principle. So here I want to show now how any size S affine DAG, which solves the search problem for the bit pigeonhole principle, must have depth at least n to the 1.5 over log S. So to instantiate the random walk with restarts approach, we are at some current linear system at the beginning of a phase. So instead of directly working with the linear system, we will have some stronger affine restriction sigma. By an affine restriction, I just mean a linear system, but now we think of it as fixing some variables as parities of the other variables which you think of as being completely free. So our affine restriction will actually be very, very structured in that we will think of some blocks as being completely fixed and the remaining as being completely free. Even among the fixed blocks, most of the bits are actually, variables are actually fixed to bits. In that sense, our affine restrictions are like sort of almost like partial assignments. But there may be some of these variables which are fixed to some non-trivial parities, which we don't know, which we have not actually assigned. And what we'll want to maintain throughout is that among these fixed blocks, irrespective of what these non-trivial parities are, like these daggers in this affine restriction, there is no possible collision among the fixed blocks. And we will also keep track of what is the set of available holes under this affine restriction. So by a hole being available, I just mean that it is not a possible hole that is used by one of the fixed blocks. And our main claim now is that as long as the set of available holes is large, then we can find a suitable node at depth square root n from the current node. So for doing this, we want some hard distribution of inputs that are consistent with the current affine restriction. So a hard distribution is simply going to be the uniform distribution on inputs where all the free blocks lie in A. Note that for such an input, the only possible collisions are the ones which occur among the free blocks. And so we can essentially forget about the fixed blocks completely. And so now we also need some sort of hardness condition to say that the new node that we have reached, the corresponding linear system, is sort of qualitatively hard in some sense. So this is a definition from EGI. So say that a linear system is good if its closure can be fixed to distinct holes in a way consistent with phi. I won't define closure formally, but informally it is the set of blocks for which the DAG knows the linear system reveals a little too much information. So the first thing we now need to show is that performing this root n step walk according to this distribution mu leads to a good linear system with some constant probability. So the intuition you should have for this is that this is the kind of bound you would get from the birthday paradox. So if you were working with just queries to bits, then this is exactly a consequence of the birthday paradox. And using ideas from lifting to parity distant trees, we show that that is also the case when parity queries are made like here. A consequence of this is that since our DAG only has S nodes, this means that during this walk, there's some linear system which is reached with probability at least 1 over S without having solved the problem. So now we would like to say that this is the node that we were looking for, because there are too many inputs reaching it, so the DAG could not have learned too much at this node. So for that, we argue separately that any linear system phi such that its rank, once we apply the substitution, is R, then the probability that it is satisfied under our distribution mu is exponentially small in R. Combining both these bounds, we get that the rank of this linear system phi v is like the relative rank after applying this restriction sigma is at most log S. And finally, we want to say that because this has small relative rank, we can actually find the kind of structured affine restriction that we were looking for without using up too many holes. So this number of holes, total number of holes used, is our actual progress measure that we are tracking. And this is what the last step lets us do. And this is basically all I wanted to say about the bit pigeonhole principle. Let me briefly mention how we prove the lower bound for the lifted Satan formula. So this is a lifted formula. So our proof strategy also involves lifting, of course. So here we start with a hardness property that we call dt hardness of the base formula. And informally speaking, dt hardness captures some conditions that we need to prove an ordinary resolution lower bound using the random walk with restarts approach. So the first thing we need is that the Satan formula on an expander is indeed dt hard. And then we lift this dt hardness of the base formula to a lower bound in res parity by using properties of the gadget. So these properties were sort of used in earlier works to prove so we had some nice distributions which also let us prove a suitable lifting theorem for parity distant trees. That is basically all I wanted to say about the proofs. Let me end with some open problems. One basic problem is to prove some restricted res parity lower bounds for the more common unary encoding of the pigeonhole principle. As far as I'm aware, nothing is known beyond the tree-like case. And of course, there remains the question of proving unrestricted res parity lower bounds, or at least going beyond subsystems that we currently know how to handle. And that is all I wanted to say. Thank you.
We have time for questions.
Yeah, so are there any ideas that might help to get beyond that squared, or it's completely unclear what we can do?
To me, it is completely unclear. I know some people have tried, but Yeah, I don't know. I don't have any ideas at the moment. Yeah.
And what would be the bounds we'll be shooting for when we are, well, ideally,
For what?
for depth, for the bound? We want to go beyond the square. How far do
I
we-
mean, so, like if you could do it, like if you could prove like some, I mean, ideally we only care about size lower bounds, but so one way to do that would be to say something like, okay, suppose we had a polynomial size proof and then you could get a contradiction by getting a super polynomial depth lower bound somehow. That would be one way. But sort of the current proofs are completely not suitable for something like this. But yeah, I mean, at this point at least, we should maybe try to go significantly beyond the kinds of things we can handle, like instead of just doing a little bit, but it's unclear how to do anything to me.
Any other questions?
Yeah, so the notion of size you have for this unconditional lower bound of like almost n squared, what is the most general notion of size you can use there? Like number of lines in proof? Or?
Yeah, here are number of lines. Yeah.
Any more questions? Let's thank all the speakers of the session.